In Azure, the concept of a virtual network, VNet, ensures that resources like virtual machines and services can communicate securely and efficiently. A VNet serves as a logical isolation of the Azure cloud dedicated to customers, providing the foundation for implementing various Azure services and controlling inbound and outbound traffic. Building on the knowledge from previous modules, where core networking terminology and preliminary Azure structures were introduced, this segment focuses on creating and configuring VNets that meet organizational and technical requirements. By developing a comprehensive understanding of address spaces, subnets, and routing within VNets, administrators can maintain effective environments that enhance security and performance. Additionally, VNets provide an extensible means of implementing multi-tier applications, supporting hybrid scenarios, and enabling consistent connectivity with on-premises infrastructures. This presentation delves into best practices for setting up and managing VNets, laying the groundwork for advanced networking topics in subsequent sections of the course. In designing Azure VNets, address space allocation is pivotal for ensuring optimal resource distribution and avoiding overlapping ranges. Azure VNets commonly utilize private IP address ranges such as 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16, which do not conflict with public internet addresses. Careful planning is essential to accommodate current and future growth to prevent running out of available IP addresses. For instance, if an organization anticipates the addition of numerous subnets or hybrid connectivity strategies, choosing a broader CDR block becomes advantageous. Moreover, the selection of an address space must reflect the organization's overall IP strategy, ensuring compatibility with on-premises networks or other VNets. By systematically mapping out address spaces before deployment, organizations can minimize network fragmentation and avoid complications during expansions. Understanding these principles enables administrators to design address allocations that meet both immediate and long-term connectivity and security needs. Subnets serve as subdivisions of a broader VNet, enabling the segmentation of resources into logical groups. This organization is instrumental in applying security policies, scaling application components, and optimizing traffic flow. When creating subnets, administrators must allocate IP ranges within the boundaries of the VNet's address space, ensuring that each subnet has a sufficient size buffer for anticipated growth. Additionally, subnetting helps limit broadcast domains and provide the structured approach for grouping similar types of workloads or isolating sensitive resources. By assigning network security groups, NSGs, and route tables at the subnet level, administrators can implement more granular control over traffic filtering and routing, enabling specific configurations. In a multi-tier application architecture, subnets frequently represent layers such as the web tier, application tier, and database tier. Adhering to best practices in subnet design ensures better security isolation, improves resource organization, and enhances the overall network manageability in Azure. Creating a new VNet using the Azure portal is a straightforward process suitable for initial configurations and quick deployments. To begin, open the Azure portal and navigate to Create a Resource, selecting Virtual Network from the list of options. Once the creation pane appears, specify a resource group, VNet name, and region to align with organizational policies and geographical considerations. Next, input the IP address space in CADR notation, which will form the basis for subsequent subnet creation. Administrators can then create at least one initial subnet or multiple subnets based on design requirements. After reviewing and validating the configuration, finalize the deployment. Once the resource is provisioned, the VNet becomes visible in the resource group, ready for additional settings such as NSGs, routing tables, or peering connections. The portal also offers a user-friendly interface for making changes to address spaces or subnets as the environment grows. For administrators who prefer automation and reproducibility, creating a VNet via the Azure CLI is a powerful approach. By leveraging command line tools, it is possible to incorporate infrastructure configurations into scripts or DevOps pipelines, thus facilitating consistent deployments across multiple environments. First, ensure the Azure CLI is installed locally or in Cloud Shell. Initiate the process by authenticating with AZ login and specifying the desired subscription. Next, create a resource group if it does not already exist, for instance using AZ group create, name RGName, location region. Then, execute AZ network VNet create, resource group RGName, name VNet name, address prefix CDR to define the VNet and address space. Additional parameters enable the immediate creation of subnets within the same command. By scripting these commands, administrators can version control networking definitions and replicate them across different projects, enhancing standardization and reducing manual configuration errors. Configuring subnets in Azure remains a critical step in structuring resources and controlling traffic. Subnets can be added during VNet creation or appended later as requirements evolve. In the Azure portal, select the VNet to which a subnet will belong. Then choose Subnets to add a new subnet with a distinctive name, range, CDR block, and optional features like service endpoints. NSGs can be associated at this stage to regulate inbound and outbound traffic. Alternatively, the Azure CLI provides a concise method via AZ network VNet subnet create, resource group, RGName, VNet name, name subnet name, address prefix CDR. This approach proves beneficial for bulk subnet creation or automated deployments. Once defined, subnets function as secure boundaries within the VNet, supporting targeted policy enforcement and network routing. Proper planning ensures each subnet has space for potential scaling, avoiding the need to resort to address migrations at later stages. Network security groups, NSGs, provide an essential mechanism for filtering traffic at either the subnet or individual network interface level. An NSG consists of inbound and outbound security rules, each specifying a source, destination, protocol, port range, and the action, allow or deny. By associating an NSG with a subnet, all resources within that subnet inherit the defined security controls, ensuring consistent protection across similar workloads. Alternatively, applying NSGs directly to interfaces allows for a more granular approach, though it may complicate management if many resources require distinct settings. Common scenarios include restricting access to administrative ports or isolating production workloads from development environments. Administrators can create and attach NSGs via the Azure portal or CLI. Monitoring NSG flow logs further refines security by offering visibility into permitted and blocked traffic, highlighting potential misconfigurations or malicious activity. NSGs thus empower administrators to implement layered security within Azure's virtual networks. Service endpoints extend VNets by providing direct, more secure access to Azure services like Azure Storage or Azure SQL Database over the Azure backbone rather than via public internet routing. By enabling a service endpoint on a subnet, a route is established from that subnet to the Azure service, strengthening the security posture and reducing latency. This configuration allows administrators to restrict access to the service only from specific VNets or subnets. For instance, an Azure Storage account can be restricted to accept traffic solely from selected subnets, mitigating the risk of exposure to unauthorized users. Implementing service endpoints often involves selecting the target service in the subnet's configuration and updating inbound firewall rules in the respective service. With data traversal staying on the Azure backbone, organizations benefit from consistent performance and improved data security. This approach aligns with compliance requirements that demand controlled communication paths for sensitive workloads. Effective DNS and name resolution strategies within an Azure VNet enable reliable communication across resources and services. By default, Azure provides an internal DNS service facilitating basic name resolution for VMs and services within a VNet. While sufficient for many scenarios, Larger enterprises might require a customized solution for integration with on-premises Active Directory domains or third-party DNS servers. In these cases, administrators can specify custom DNS server addresses when creating or updating a VNet, ensuring that domain names are resolved in a manner consistent with organizational policies. FQDN resolution within VNets is crucial for seamlessly connecting application tiers, microservices, or multi-region deployments. Administrators should plan DNS structures carefully, as advanced scenarios may involve split-brain DNS or specialized record management. Monitoring DNS query success rates and diagnosing potential resolution conflicts is equally vital. By adopting a logical approach to DNS, organizations ensure efficient resource discovery and maintain a stable networking environment. Azure VNet peering connects two VNets, enabling resources to communicate using private IP addresses as if they were part of the same network. This method offers low latency, high bandwidth interconnectivity without requiring additional gateways, simplifying cross-VNet traffic. Peering is commonly employed to link different departments, environments, or regional deployments. To configure peering, administrators must establish a peering relationship from both VNets, specifying the desired connectivity options, such as whether traffic is allowed from linked VNets or forward traffic to remote gateways. It is critical to ensure that the address spaces of the VNets do not overlap. Otherwise, peering cannot be established. Once established, peering can be monitored to track data transfer and ensure stable connections. Unlike VPN tunnels or ExpressRoute connections, peering leverages the Azure backbone, resulting in minimal overhead. Peering thus becomes instrumental in building complex distributed environments or seamlessly merging resources during an organizational consolidation. VNet to VNet connectivity provides an additional layer of secure communication between Azure virtual networks, especially when regions or subscriptions differ. Unlike peering, which is often easier to set up, VNet to VNet connectivity may incorporate VPN gateways to encrypt traffic. This approach is especially relevant when organizations require site-to-site VPN encryption standards or plan to integrate on-premises networks with multiple VNets. The process typically involves creating VPN gateways in each VNet and configuring them with shared keys and connection parameters. By establishing IPsec tunnels, data flows securely over the Internet or ExpressRoute. This design can help meet compliance requirements for data in transit encryption. When selecting between peering and VNet to VNet gateways, consider factors such as encryption needs, cross-subscription connectivity, and the desire to forward traffic to on-premises networks. Proper planning of gateway sizes and IP address assignments ensures that potential throughput and concurrency demands are effectively met. Configuring IP addresses for Azure resources complements the broader design of VNets and subnets. By default, Azure assigns dynamic private IP addresses to virtual machines, ensuring they remain reachable within the network. However, certain workloads or services may necessitate static or reserved IP addresses to maintain stable connections or comply with licensing. When using the portal, a static private IP can be assigned under a VM's network interface settings. Automated approaches in Azure CLI or ARM templates further streamline IP assignment, beneficial in larger environments. Additionally, public IP addresses may be allocated to allow external connections to specific services, with features like static allocation or domain name labels. Administrators must monitor the IP address usage to avoid conflict or depletion within subnet. The holistic management of IP addresses, both private and public, aligns with overarching VNet structures, ensuring resources remain reliable, discoverable, and consistent with organizational governance models. Effective monitoring is integral to maintaining healthy VNets and subnets. Azure offers various tools, such as Network Watcher, to provide insight into traffic flow, connectivity status, and diagnostic logs. With Network Watcher, administrators can run tests like connection troubleshoot to identify routing issues or confirm endpoints can communicate as expected. Flow logs within network security groups reveal which traffic is passing or being blocked, highlighting potential misconfigurations or suspicious activity. Metrics on data transfers, latency, or packet drops enable data-driven optimizations and capacity planning. Integrating Azure Monitor with VM or container metrics extends visibility into network resource usage and performance. Additionally, alerts can be configured to notify teams of abnormal conditions, such as high CPU usage on gateway VMs or unexpected inbound traffic spikes. By proactively examining these metrics and logs, administrators safeguard the reliability of their virtual networks and promptly address potential issues. Virtual networks form the backbone for many Azure services, allowing them to function in isolated or hybrid scenarios. Services can be deployed directly within a subnet, enabling direct communication with VMs, containers, or other resources without leaving the private IP space. For example, Azure App Service Environment can be configured in a VNet for hosting web applications under tighter security constraints. Likewise, Azure Kubernetes Service, AKS, can be integrated with a VNet to control traffic to and from containerized workloads. Additional features, such as Private Link, extend connectivity by mapping services like Azure Storage or Azure SQL into the VNet, protecting data traversal from public exposure. As organizations scale their cloud usage, strategic integration ensures consistent network policies across diverse workloads, unifying application access and strengthening security. Careful design and planning remain crucial in achieving a robust environment that aligns with both performance objectives and regulatory mandates.